So the last speaker of this morning session is Tommaso Nello, who will talk about unveiling the periodic variability pattern for multi-wavelength light emission from blazar PG1552.
Hi everyone, my name is Tommaso Nello. I am a PhD student at Sapienza University. I work also with the very high energy group at the Monte Pozzo Observatory in Rome. And today I will talk to you about the multi-wavelength variability emission of the blazar PG1553+113. As you all know, in particular, a blazar is an active galactic nucleus observed along the line of sight of the superluminal jet. And this jet predominates over all the other components. A typical spectral energy distribution of blazar is composed of two well-defined humps, which are due to the synchrotron emission, the first one, and to the inverse component effect, the second. This is the set for the G1553, and we can see that this is the region of the X-ray. And when we studied X-ray, we studied the synchrotron emission in this case. PG1553 is a blazar, high energy PKL lac, with a redshift not well defined. It's famous because it's already been observed at different wavelengths with a period about 2.2 years. This is the light. Sorry. This is the night of the gamma ray Fermi satellite, and it's evident periodicity of 2.2 years. And seeing that this periodicity is also present in other wavelengths. To explain this behavior, have been proposed some models, and there is a periodicity in multi-wavelength light curve. An explanation might be that inside this object there is a system of two supermassive black holes spinning around each other in different ways. And this model from Sobacki provides that one of the supermassive black holes carries a jet that proceeds. And this scenario is in agreement with the data of Fermi satellite and from optical data from Tuarla Observatory. To better understand the structure and the processes at work, we analyze optical, ultraviolet, and X-ray data from Swift satellite. And we analyzed the data from 2012 to 2022. As we can see from the multi-wavelength light curves, there is a wide variability, simultaneous and multiple peaks in the optical, in the ultraviolet bands. And it's clearly that the optical and ultraviolet bands follow the same trend, while for the X-rays it's not so evident, but they are related in some way. And we study the correlation between these bands, and we found evident correlation between optical and ultraviolet bands, and a moderate correlation between optical and X-ray bands and the ultraviolet and the X-ray bands. We study also the photon index flux ratio to better understand which process start to work in this object. And we found anti-correlation and then harder when brighter behavior common in blazars. This behavior means very probably that we are in presence of synchrotron emission. to investigate the possible periodic behavior on the X-ray, ultraviolet, and optical emission in this object, we employed the long-scale method, that technique used for analyzing unevenly sampled time series data to identify periodicity within data. And this method calculates a periodogram, a measure of the power spectrum at different frequencies. The periodogram quantifies the strength of periodic signals in the data at various frequencies. We apply this method to X-ray data, Swift-XRT data, and we found a peak in frequency that corresponds to a period of 1.4 years. In this plot, there are also other peaks of lower age, which could mean that the period could not be unique, but that we are in presence of several periods which could be maybe harmonics. This is the superimposition on the data of a sinusoid with the found period. And we can see that the peaks of the sine function are in good agreement with the flaring state of the source. We apply the Lomskargol method also to ultraviolet and optical bands, for example, W2 band, and we found a period of 2.1 years. This is the superimposition of the model of the sine function to the ultraviolet data. This is the optical V band, and also we found a 2.1, a period of about 2.1 years. And this period in ultraviolet and in optical bands is the same period that found other groups in the literature. In addition, we analyze our data also with the Chronos, software Chronos, a package created by NASA ESA, designed for the analysis of high energy statistical data. And with the power spectrum method, we found the same behavior and the same period that we have found with the Lomskargol method. And we applied also to this method to the optical and UV bands, and this method returns the same result already found by previous researchers at this wavelengths. With the AF search method of the Chronos, we can calculate also the uncertainty of the period. This uncertainty is about 0.2 years. A possible scenario is, so we found two different periods. A period in gamma ray, in ultraviolet and optical bands, about 2.2 years, and a different period in the X-ray bands, about 1.4 years. A possible explanation is that we are in presence of two supermassive black holes. The secondary black hole orbits around the main central engine and perturbing the X-ray emitting region with this period. And the second period is due to the jet carried by the main black hole that proceed with a different period of 2.2 years. In the future, would be interesting to study the polarimetry of this object, for example, using XP data, and also apply the same reasoning to the Fermi gamma ray light curve. That's all for the moment. Thank you for the attention.
Questions? I was curious to know when you show the fitting of the sinusoid, the other pattern that seems to be just this light, yes. There is a slight shift in time. So I was wondering if there are additional frequencies that you see in the spectrum.
This
Yeah, in the if you have just
it is a possibility. I don't know if it's really so. It's only a possibility.
So, have you done any modeling against the red noise process to actually assess the statistical significance properly with long-scale? Because you have to do that, otherwise you're just assuming the white noise process.
With long scale, please.
So, in the literature, there are several papers which describe how to use long-scale properly when assessing the significance of periodicity that you find in AGN or potentially find in AGN. You have to compare it not against the white noise process, but you have to compare it against the red noise process. So you can't just take the peak of you can't get the significance from the peak stuff in long scale. You have to consider a background process which is correlated.
No. Only we use the long scale because it is good for analyze unevenly sample time series.
Yeah, there are a couple of well-documented papers which describe this, and there's also several code repositories on GitHub, so you don't even need to write the code yourself. It's all out there. You just need to.
Okay.
I would suggest having a look at it before you attempt to publish this.
Thank you. Maybe in the future.
Any other question? Okay, then let's thank